Good morning, students. In the present class, we discuss about what is interference of light, how Thomas Young observed the interference of light, and what the interference pattern consists of. Here, the interference pattern consists of bright and dark regions. When bright region is formed, when dark region is formed, and what is the width of that bright or dark region. Now we know that first of all, interference of light means superposition, interfere, superposition. So whenever two or more light waves having the same amplitude, same wavelength, and having a constant phase difference between them superimpose with each other, the redistribution of light energy takes place in such a way that at some points, at some regions, the light energy is maximum, whereas at the other regions there is no light energy. That means due to the superposition of the light waves having same amplitude, same wavelength, and same phase difference or constant phase difference, alternate bright and dark regions are formed. This phenomenon is called interference of light. Okay, so to observe this interference of light, the two light waves must have same amplitude, same wavelength, and maintain a constant phase difference or zero phase difference between them. So that two light waves must be obtained from a single source only. Even though the two light waves emitting from two different sources having same amplitude, same wavelength, they do not maintain a constant phase difference between them. So to maintain a constant phase difference between them, the two light waves must be obtained from a single source. So this Thomas Young observed that interference pattern by using the apparatus that he used a opaque screen which is having a small slit in it. Whenever this slit is illuminated with the monochromatic source of light, this slit produces the light. Only the light waves are emitted from this slit, so that slit act as a source, and these waves are spread towards the another screen having another opaque screen having two slits S1 and S2, which are placed at equal distance from S0, So these waves, the wave emitting from S0 illuminate on this screen and produces the two waves. These, and here the waves are produced from these screens. These waves spread outwards and they undergo superposition and forms the interference pattern on the screen. The point where the two waves undergoes superposition in phase, and if crest of one wave falls on the crest of another wave, then we get the bright fringe on the screen. Ala kakunda, if the crest of one wave falls on the trough of another wave at the point, then a dark fringe is formed. And the conditions for the formation of bright fringe and dark fringe is that whenever the path difference between the two light waves reaching the point on the screen is equal to m lambda, whenever the path difference between the two light waves reaching the point where they undergo superposition is m lambda, we get the bright region where m equal to 0, 1, 2, 3, and whenever the path difference is 0 or lambda, 2 lambda, 3 lambda, 4 lambda, and so on, then the waves undergoes superposition in phase. That means crest of one wave falls on the crest of another wave, the trough of one wave falls on the trough of another wave. Due to that superposition, due to the constructive superposition, the resultant amplitude is maximum and the intensity of light is maximum at that point. So bright region is formed. Lagakunda, if the path difference between the two light waves is m plus 1 by 2 into lambda, where m equal to 0, 1, 2, 3 and so on. Then they undergo destructive superposition. That means crest of one wave falls on the trough of another wave. Due to that destructive superposition, the resultant amplitude becomes 0. As a result, the intensity of light becomes 0. Like this, whenever the path difference between the two light waves is 0, lambda, 2 lambda, 3 lambda and so on, m lambda, we get the bright fringe. If the path difference between the two light waves reaching the point on the screen is m plus 1 by 2 into lambda, we get the dark fringe. Okay? On the screen, alternate bright, dark, bright, dark, bright, dark fringes are formed on the screen. Now we are going to obtain an expression for the width of that bright or dark fringes. Here, let it be, I will redraw this one. Bright fringe, dark fringe, bright fringe, dark fringe, bright, dark, bright, dark, bright, dark, like this. These are the fringes formed on the screen. Now we want to find out the width of this bright fringe and width of dark fringe. So to find the width of dark fringe, if we calculate the distance between two successive bright fringe, the distance between two successive bright fringe gives the width of dark fringe. Similarly, the distance between the two successive dark fringes gives the width of bright fringe. That distance between two successive bright fringe or dark fringe is called fringe width. Is called fringe width, denoted with beta. Denoted with beta. Now, for the sake of convenience, I can represent the distance between the two slits as large. This is S1 and this is S2. Let d is the small d is the distance between the two slits, distance between the two sources, the two slits, and this is the screen which is at a distance capital L from the slits where we observe the interference pattern. This is the screen. On the screen we observe the interference pattern. Now let O is a point on the screen which is at equal distance from S1 and S2. O is a point on the screen which is at equal distance from S1 and S2. Now the light waves which reach the point O has to travel equal distance. So there is no path difference. The path difference between them is 0. Automatically a bright fringe is formed here. In the interference pattern, the central fringe is the bright fringe. Now we take a point P on the screen which is at a distance x, which is at a distance x from the center, which is at a distance x from the center of the screen. Now if the path difference between the two light waves reaching the point is m lambda, the point P will be bright fringe. If the path difference between the two light waves reaching the point P is m plus 1 by 2 into lambda, dark fringe is formed at this point. Now the light coming from S1 and S2 reaches the point P, and where they undergo superposition forms either bright fringe or dark fringe depending upon the path difference between the two light waves at that point. Now here we know that the light emitting from S2 has to travel more distance than the wave coming from S1. So there exists certain path difference between the two light waves. So that path difference is, and if you draw a perpendicular from S1 onto the second beam, this gives the path difference, the extra path travelled by the light wave emitting from S2. Now this rays makes an angle theta with the horizontal. These rays making some angle theta with the horizontal. So by symmetry, here also it is having the same angle theta. Now we want to find out this path difference. Okay, from this triangle S1 S2, let it be SA, S1 S2 A, this is opposite side, adjacent side, hypotenuse, opposite side, adjacent side, hypotenuse. Now we want path difference delta, opposite side. So from the diagram, from the triangle, sin theta equal to opposite side delta by hypotenuse d, where d is the distance between the two light sources, the distance between the two slits, and from this delta equal to d sin theta, this is the path difference between the two light waves. Suppose if the screen is at large distance, then this angle theta becomes very small. We know that for smaller values of theta, sin theta is nearly equal to theta and tan theta is nearly equal to theta. So from that we can write sin theta is nearly equal to tan theta. So therefore delta equal to d into tan theta, path difference delta equal to d into tan theta, because for smaller values of theta, sin theta is nearly equal to tan theta. Now from this triangle, here also the angle is same theta. So tan theta equal to okay, in this triangle, from this triangle, this is opposite side, this is adjacent side, and this is hypotenuse. Tan theta equal to opposite side and x by adjacent side L. Now the distance between the slits and the screen is L, x by L. Therefore path difference delta equal to d tan theta, then delta equal to d into tan theta is x by L. This is the path difference between the two light waves reaching the point on the screen which is at a distance x from the center. Now we know that suppose if the point P is bright fringe, if the intensity at the point P is bright fringe, the bright region, then what is the conditions for formation of bright fringe? Whenever the path difference between the two light waves is equal to m lambda, whenever the path difference between the two light waves reaching a point on the screen is m lambda, where m equal to 0, 1, 2, 3, and 0, lambda, 2 lambda, 3 lambda, 4 lambda, and so on, bright fringe is formed. So from this we know that path difference delta is d into x by L, dx by L equal to m lambda. From this x equal to m lambda L by d, where x is the position of bright fringe and m is the fringe number, first bright fringe, second, third, and so on. Lambda is the wavelength of light used, and L is the distance between the slits and the screen, and d is the distance between the two slits. Again I will redraw the diagram simply. This is the distance between them, and this is the screen, and this is the center O, and P is a point which is at a distance x. Suppose x1 is the distance of first, this is central bright fringe, first bright fringe, second bright fringe. Suppose for the first bright fringe, if you substitute m equal to 1, if you substitute m equal to 0, that is a central bright fringe. If m equal to 1, first bright fringe, m equal to 2, second bright fringe. So for the first bright fringe, then from this x1 equal to lambda L by d. This is the position of first bright fringe. 0, first bright fringe x1, second bright fringe x2. Suppose, and similarly the position of the distance of second bright fringe from the center is x2 equal to 2 lambda L by d. If you substitute m equal to 2, we get the position of second bright fringe from this center. From this, x2 minus x1, x2 minus x1 equal to, that means the distance between the second and first bright fringe gives the width of the dark fringe. Width of the dark fringe. Fringe width chepnam. The distance between two bright or dark fringes is called fringe width. x2 minus x1 is 2 lambda L by d minus lambda L by d. From this we get lambda L by d. This is the distance between two successive bright fringe. Now the distance between two successive bright fringe is the width of dark fringe. Therefore, fringe width, dark fringe width beta equal to lambda L by d. Lambda L by d. Let it be equation 1. Let it be equation 1. Suppose if the point P is dark fringe, at the point P, if the dark fringe is formed, then for the formation of dark fringe at the point P, the path difference between the two light waves must be equal to, the path difference delta is equal to m plus 1 by 2 into lambda, where m equal to 0, 1, 2, 3, 4 and so on. If you substitute m equal to 0, the path difference is m plus 1 by 2 becomes lambda by 2. If you substitute m equal to 1, 3 lambda by 2, 2, 5 lambda by 2. And whenever the path difference between the two light waves reaching a point on the screen is lambda by 2 or 3 lambda by 2 or 5 lambda by 2, 7 lambda by 2 and so on, the dark fringe is formed at that point. Then we have path difference. We know that whenever the path difference between the two light waves reaching a point is equal to m plus 1 by 2 into lambda, we get the dark fringe. From this, we know that fringe width, path difference delta equal to dx by L, that equal to m plus 1 by 2 into lambda. From this, x equal to m plus 1 by 2 into lambda L by d. This is the x. Here x equal to distance of the dark fringes from the center. Distance of the dark fringes from the center. Suppose if you substitute m equal to 1, we get the distance of first dark fringe. M equal to 2, distance of second dark fringe. Suppose therefore x1 equal to distance of the position of first dark fringe from the central fringe is 1 plus 1 by 2. 1 plus 1 by 2 into lambda L by d. We get 3 by 2 into lambda L by d. 3 by 2 lambda L by d. Similarly, the position of the distance of second dark fringe from the central fringe is x2 equal to, if you substitute m equal to 2, we get 2 plus 1 by 2 into lambda L by d. That equal to 5 by 2 into lambda L by d. Now, this is from this x2 minus x1. x2 minus x1. The distance between the two dark fringe, first dark fringe, second dark fringe. If we subtract x2 minus x1, we get the distance between two dark fringe, which gives the width of bright fringe, the bright region. So 5 by 2 into lambda L by d minus 3 by 2 into lambda L by d. 3 by 2 lambda L by d. From this expression, x2 minus x1 is called fringe width. 5 by 2 lambda L by d minus 3 by 2 lambda L by d. We get 2 lambda L by 2d. 2 lambda L by 2d. From this 2 gets cancelled. We get fringe width lambda L by d. This is the bright fringe width. Let it be equation 2. From equation 1, what is the dark fringe width? Beta equal to also lambda L by d. That means in the interference pattern, the width of bright fringe is equal to the width of dark fringe. The width of bright fringe is equal to the width of dark fringe, and that fringe width depend upon the fringe width is from this expression. So finally the expression for fringe width, whether it is bright fringe or dark fringe, beta equal to lambda L by D, where lambda is the wavelength of light used, L is the distance between the slits and the screen, and D is the distance between the two slits. From this, the fringe width is directly proportional to wavelength of light. If the wavelength of light is more, the fringe width is more, and the fringe width is directly proportional to the distance between the slits and the screen. Directly proportional to the distance between the slits and the screen. And if the distance is more, the width of the fringes formed on the screen is more. That means we can observe the clear interference pattern on the screen. And the fringe width is inversely proportional to the distance between the two slits, two light sources. It is inversely proportional to the distance between the two light sources, like the two slits. From this, if the distance is less, then the fringe width is more. That's why, for the superposition of two light waves, the two light sources must be very close to each other. When they are very close to each other, there is a large chance of superposition of waves and forms the perfect interference pattern. అందుకే ఈ టూ సోర్సెస్ మధ్య ఎంత తక్కువ డిస్టెన్స్ ఉంటే అంత బాగా ఇంటర్ఫరెన్స్ ప్యాటర్న్ వచ్చేసి ఏర్పడుతుంది. దిస్ ఇస్ ద expression for fringe width of interference pattern formed.